So let's start the second session of this workshop. We have Aschenauer from Brookhaven National Lab, and she will tell us about the experimental program, Detector for EIC, and the R&D.
Yeah, so thank you very much for the invitation, and that I can talk about the detector, where the project stands, because that is important as well if you want to join, and also a little bit about the accelerator and how the interplay between the accelerator and the detector is. And I was asked to focus mainly on the detector and the R&D, and that is what I will do. We have to click on it, maybe. Okay, can I? No. Yes. Okay, so for everybody who is not yet familiar, the EIC on one slide. So the EIC is a high luminosity polarized electron-proton ion collider with a wide range in center of mass energy. What is special? It is the only new collider to build in foreseeable future, and that means the next 10 or 20 years. It allows to remain at the frontier of accelerator science and technology. It has a factor 100 to 1,000 higher luminosities than the only other electron-proton collider existing in the world, which was HERA. Both the electrons and protons and light ions are polarized. We have, yeah, okay. Very good, thank you. So we have the higher luminosity. We have nuclear beams, which HERA didn't have. If we compare to fixed targets like JLab, COMPASS, Hermes, then we have at minimum 2 decades more increase in kinematic coverage in X and Q square. We have a really interesting science program, which you heard some of from Christine already. Good. So we have a nice science program, which I will come to, and we really built a state-of-the-art general purpose collider detector. So now it doesn't move again. We get it, we get there. Hardware is sometimes difficult. Okay, so now the golden process which we are using is deep inelastic scattering, and we use this because the probe, the electron really has unmatched precision because it uses the electromagnetic interaction, and it has actually no structure, like if you collide protons and protons. I have 2 beams which have a high structure, and that actually really helps to have a direct model independent determination of the parton kinematics of the physics process. So you have your electron, which emits this virtual photon. That one then interacts with the partons inside the proton or the nuclei, and the reaction is governed by here this kind of equation. So you have Q square, which gives you the resolution power. You can think about like a Q square is 1 over the wavelength of this virtual photon. Then you have S, the center of mass energy, X, the fraction of the parton kinematics carried by the struck quark, and then you have Y, which gives the inelasticity. And there we, the movie doesn't play. Okay, we have a large kinematic coverage from 30 to 140 GeV, because we really want to access X and Q square over a wide range. Because if you look at high X, the proton actually looks like a valence quark, and at low X, it is completely dominated by gluons. And we would really like to see how this transition smoothly goes from high to low X. So here you see the kinematic coverage of the EIC. So we cover from here this line up to down here to 10 to the minus 5. You see that compared with polarized EP and PP kind of data. You see the fixed target kinematics. You see here's the RIC data and the W data from STAR. And you see very nicely that the EIC actually really covers the entire region and actually extends it significantly to lower X, which is interesting, particularly for some of the physics program. If you want to go to the lower X, you have to increase your center of mass energy. And if you want to increase in Q square, then you need to increase your luminosity because high Q squares, the cross section are very low. And you have to increase your center of mass energy to reach really the highest Q squares. So for the physics program, just on one slide, we want to really understand how the C quarks and the gluons and their spins are distributed in space and momentum. So TMDs and GPDs are very important for this. We want to understand how the nucleon properties really emerge from the partons and from their interactions, and that is particularly then also part of the mass of the proton. And then we take nuclei, and then we change actually what happens to what we see in the proton if we measure the same quantities on nuclei. How is the nuclear interactions actually governed by the gluons and quark-gluon interactions, and how do the confined hadronic states actually emerge from the quarks and the gluons. And then last but not least, we have actually within nuclear beams the highest nuclear densities, and there we can actually really study whether we see non-linear QCD effects, so that the gluon emission gets balanced by gluon recombination, which very often is referred to as saturation. So if we have this physics, then we can kind of correlate it directly to properties of the accelerator. So if we really want to map out the nuclear structure from high to low X, then we need this wide center of mass energy. If we want to access a spin structure, we want to use spin as a vehicle to study spatial and momentum distributions. And we want to understand initial and final states to probe quark-gluon structure in nucleon, and interaction and like nuclei. Then we need actually polarized beams, both the electrons and hadron beams, so proton on helium-3. If we want to study saturation, we need the nuclear beams. If we want to map really spatial and momentum structure, there you have to be in 5 dimensions, and we want to access rare probes. That is why we need really this high luminosity of 10 to the 33 to 10 to the 34. And if we really want to do spatial imaging, we need very good acceptance for particles, and I will show this later, which are scattered under very small angles along the beamline, and to detect them that we really can do imaging in the spatial direction. So let's first look a little bit to the accelerator. What is special at the EIC accelerator? So we have some design goals. I said already the high luminosity, which leads to 10 to 100 inverse femtobarn per year. The polarized beams, which then also immediately requires that you have very high precision polarimetry. The large center of mass energy, and the different one I will show you, really has an impact on the acceptance of your detector. So you have to design your detector so that it can scope with such a large variety of center of mass energies. The ion species require actually forward detectors integrated into the beam lattice. You need really good background conditions, and I will come back a little bit to this. And the machine can actually accommodate a second interaction region, but right now the project actually only has integrated one here at IR6, which the EPIC experiment is actually located. The beams we are kind of colliding, the protons are 41, or the ion beams 41 GeV, and then any energy between 100 and 275. And the electron beams are continuous between 5 and 18 GeV. So as a machine is based on the hadron side, on the very well-maintained and well-performing RIG machine, which some of you are familiar with if you're working either as Phoenix or Star. So we have a hadron storage ring, which can do this energy. We have superconducting magnets, which we are reusing. We kind of increase actually the beam current by a factor of 3 compared to RIG, and we increase the number of bunches enormously. We have 120 right now, and we will go to 1160. We change actually how the beams are looking, and we have a new way to cool the beams, which we are developing, which is the strong hadron cooling. For the electron storage ring, so here you have 2.5 to 18 GeV. We have extremely high beam currents, 2.5 ampere in the machine. That is actually really something which is a lot. That is as much as the B factories have. And we have to inject polarized sponges because the electrons have to be polarized, and we have actually also spin directions in the machine. For that, we are building actually a very specialized injector, a rapid cycling synchrotron, which has high periodicity, and that actually gives you then the spin transparency and creates a polarized beam. And then the most demanding area is the interaction region, where we have very high focusing superconducting magnets. Every single one is a specialized one. We have a crossing angle. That is the first time in the world that a machine runs with a big crossing angle of 25 millirad. And if you want to then have also high luminosity, you need crab cavities that you get back to a head-on collision, spin rotators, and we have the forward hadron instrumentation. And if you look here, that leads then actually over the center of mass energy to this luminosity, and you see that actually over a wide range, it's basically flat and close to 10 to the 34. And at the very highest luminosity, it drops again, and that has to do that we have to limit actually the synchrotron radiation power of the machine. So if we compare a little bit the EIC with the LHC and RIC, so then the first thing is we don't collide the same species, we collide electrons and hadrons. That automatically leads to that we have beam backgrounds from both of the beams. And for the DIS, what you have to keep in mind is that the cross-section of the interaction is smaller than the cross-section of the backgrounds. So you really need to kind of do a good job in keeping your backgrounds under control. What is nice is that different to the LHC, we don't have a pileup. We have asymmetric beam energy, so you have a boosted kinematics. So the particles go either very forward. So that means that you need really a large coverage in rapidity. In LHC, where you collide, and also at RIC, the same beam energy is most of your activity is at mid-rapidity. Bunch spacing 10 nanoseconds compared to the 25 nanoseconds, the big crossing angle. We have a very wide range of center of mass energies, a factor of 6. The LHC does a factor of 2, and only RIC is more can do more, 26 in AA and 8 in PP. As soon as you have polarized beams, your statistical uncertainty is not only determined anymore by the luminosity, but actually also by the polarization degree which you have in your both beams. And all of this needs to be kind of integrated in your detector and what detector technologies you're choosing, because what is good for LHC is not necessarily good for the EIC. So then I told you we will have 2 interaction regions, and I want to talk a little bit about it because there's a lot of rumors going on what is happening between the 2 interaction regions. So one is sitting here where star is sitting, the other one is where as Phoenix is right now. They have the same accelerator highlights and challenges. There's no difference between them. They will have different crossing angles. So the one which we are building right now has 25 millirad, the other one has 35 millirad. So we said it will be more difficult to get to a high acceptance at very high rapidity, so very close to the beam. There will be, because of this, different blind spots, which means that you have different far forward detector acceptances. They will have the same luminosity at both interaction regions. It's not that one is a high or low luminosity interaction region. It's identical because they are operating in the same machine. They have the same center of mass energy coverage. It's not that one is low center of mass, the other one is high one. And then for the IR design, for the current one, we have a coverage from 200 MeV to 1.3 GeV in the forward instrumentation. As a second IR, if we are lucky and we can build the magnets, we can have a secondary focus, and that means we can go down to PT of 0. And for the experiments, you can design 2 experiments, and there comes in complementarity through choosing different subdetector technologies. But overall, the 2 interaction regions are not widely different. So if you hear something else, That's not correct. Okay, so let's go to the detector. And before we discuss this, I want to talk a little bit about the experimental program. And we have been very busy since 2020 to actually really set up the experimental program. We started with a call for expressions of interest. So basically launching and asking, okay, would you like to work with us on the EIC? And we also received an expression of interest from India. We got a lot of responses and we were really very happy. And based on that responses, we felt comfortable that we could call for collaboration proposals for the detectors. We did this in 21. We got then 3 proposals. They were kind of due by December, so basically a little bit less than a year. Then we had a high-ranked committee which kind of was choosing one of the proposals, and the baseline technology was, baseline proposal was chosen was EDGE, that was in March 2022. But then, of course, we cannot say, okay, to the other people, we are not interested anymore that you work with us. So we went actually to a process to consolidate the 2 big proposals, which were EDGE and Asina, and that started in spring and actually finished in summer in 2022, where we formed actually officially the EPIC collaboration with 160 institutions, and I show you how we have, and then we kind of ratified as a charter, elected leadership. We formed a resource review board. If you're familiar with CERN, that is something which you have there as well, where everybody who contributes sits on one table and has a say. And we made all the technology choices for the experiment by spring last year. So very busy, but also very nice. So if you look to the worldwide interest, so we have the EIC user group, which was very instrumental actually in as we were setting up for the EIC. We have 14,400 collaborators all over the world, experimentalists, theory accelerator scientists, and you can see that actually there's a large contribution from North America and then equally from Europe and Asia. And you can see here how it's distributed over the world. The EPIC collaboration, I told you, was formed fully by December 2022. The collaboration leadership, John Lajoie from Oak Ridge and Silvia Della Torre as deputy spokesperson. EPIC is actually soon becoming a recognized experiment at CERN also. That presentation is happening at the 8th of February, and we think it is a slam dunk that gets actually approved. And right now we have 171 institutions from 24 countries, and we have actually 30 new institutions since July last summer. And you see here how they are distributed over the world. And of course, we are very happy to have a lot of collaborators also from India. So that is something which we are really enjoying that has worked out. So now, if we look to the scope for the experimental program, so I told you the high luminosity, the high polarized beams, and then that automatically means that electron and hadron polarimetry is part of the experimental scope. So you need actually very high precision polarimeters which have a systematic error of 1%. The center of mass energy means that you have the large detector acceptance. The asymmetric beams requires that you have an asymmetric detector with a barrel and 2 hadron end caps, and I will talk about that a little bit more in detail in the next slide. We have equal coverage from -4 to 4 in rapidity for tracking, particle identification, electromagnetic and hadronic calorimetry. We have high precision, low mass tracking, good electron-hadron separation because we need to identify the scattered electron very precisely. And we have good separation on track level for electrons, and that should be a pion, kaons, and protons. The science program actually requires very high momentum resolution. And the EDGE proposal, for example, came in to reuse the Barber magnet from S Phoenix, and it turned out if you put it actually in an EIC detector, that will not work. So we are actually building a new 2 Tesla magnet so that we can get actually the momentum resolution which we need. And that's quite challenging because the there hasn't been built a large magnet for an experiment since CMS and Atlas. And funny enough, the world has lost some capability to do some of the things. So it's actually very nice. For the imaging program, we have this ion species, and they mean that you need to integrate detectors in the forward-going and the backward-going direction. So the whole total detector is actually plus minus 80 meters. We do streaming readout, and I come to this for the highest scientific flexibility. The detector is very compact, only 9.5 meters long. So integration is key. So I have really meetings where I discuss about whether I get this millimeter or somebody else gets it. Good background conditions, and I will not talk about this, but if you are interested here, I gave you a link to a presentation I gave about what the backgrounds are. And in total, we have 25 different subsystems with different technologies. So this is actually pretty demanding and more than some of the big collider detectors have. So now let's look a little bit why the detector has to be so asymmetric. So here you have your beam pipe, you have your electrons coming in from the right, the protons or the ion beams from the left. They collide in the middle. And then if you want to kind of detect particles or hadrons from a high X interaction, then you have to actually have detectors which are in this region here. Medium X goes into the main detector, and then low X goes into the electron going direction. And then the same with the scattered electron. If you have low Q square or high Q square, you either have to be very close to the outgoing electron direction, or you go into the mid-rapidity range of the detector. So if I do inclusive DIS, where I want to only detect the scattered electron, then I need a detector which basically fills this type of rapidity range. So you would have half of your barrel and some end cap. But as soon as I want to look to the final state, of course, I need to complete my barrel because I go to the other side of the rapidity, and I need also an end cap for the hadrons which are coming from high X. And then if I have exclusive reactions which are critical for the spatial imaging of particles, then I actually need a lot of these forward detectors which are integrated in the beam pipe, because I need to detect this proton or other particles which are produced under very small angle, which are going along the beamline. So here just some details about the detector. So Marco is the name of our magnet. It's a 2 Tesla magnet. It's built on a copper conductor. The parameters are actually pretty safe. The density of the magnet is less than a radiation length, which is very nice and important because the particles have to reach the hadronic calorimeter behind this. And with kind of designing the magnet, and I will come back to this, the magnet is actually ready to go into construction. We had also to kind of really pin down all the flux return of the around the magnet, which has consequences because the hadron calorimeters are actually the flux return. So then let's look to the tracking detectors. Here you see the tracking detectors are, of course, the heart of the EPIC experiment. Here you kind of see it zoomed out. We have 2 different ones. We have tracking detectors which are based on this monolithic active pixel silicon tracker, so MAPS. You see them here in green. And then we have multi-Bedangadas detectors, which are kind of surrounding the MAPS tracker, which are here in blue. And it's basically as larger you go in radius, as more silicon you need, and as more expensive it becomes. So you go to a different technology. If we look to the MAPS, that is actually a really kind of fascinating technology. We work very closely with ALICE, the ITS3 program. Actually, we are signing an agreement with them at the moment. And the microvertex layers here, they are basically looking like a piece of paper which you surround the beam pipe with, and it's all silicon. So very fascinating. And if you look then to the outer layers, so some MPGDs, there we have 2 different technologies. So the ones which are closest to the interaction region are actually micro-arwells. And then the outer ones, so these ones are micromegas and the outer one is micro-arvals. And actually the micro-arvals is a completely new technology which has never been realized. And we have also disks in this. And the same is true for the maps. Nobody has built actually maps disks like the green ones here in the world. So that will be also completely world first to be done in EPIC. So then we go to calorimetry. I told you we have the same coverage for electromagnetic and hadronic calorimetry, electromagnetic here in red and hadronic in blue. And then if we look in the electron going direction here, we have a lead tungsten calorimeter. That is lead tungsten because it gives us the highest resolution possible, 2% over square root E. And we read it out with PSIPMs, which is the first time that actually really happens anywhere. Then if we look in the barrel, very interesting calorimeter. So it is a lead sci-fi matrix. And then we basically build shells out of lead scintillating fibers. And then we insert astropix maps, which actually give us a perfect imaging of how the shower and the particles go through there. So also a completely new technology. And then in the forward-going direction, the electromagnetic calorimeter is some technology which was actually developed for the EIC. So it's tungsten powder with scintillating fibers kind of embedded into this, and I have a little bit more read out with PSIPMs. And the technology development was so successful that Phoenix said, we take it and we put it in our barrel calorimeter. Then if we look to the hadron calorimeter, also very nice, the forward one, very highly segmented longitudinally. It's a steel scintillator sandwich. But what is very nice is that we embed the silicon photomultipliers in the scintillator and read them out. So you have a very high granularity, and it's basically the first time that this Callis inspired design is realized in a detector. Then the barrel calorimeter, we reuse the one from Phoenix, and the forward one is a simple steel scintillator sandwich because it's mainly a tail catcher, not measuring very precisely the energy. And if you look here, you see actually that is for the electron calorimeters, you see the excellent energy resolution which we have for all the regions which we have inside the detector. Particle identification, absolutely crucial for the EIC program because we want to do semi-inclusive physics, and for that you need kaon, pion, and proton identification. So if you want to do that, here you see actually the momentum range over the rapidity for the highest center of mass energy. And what you can see, if you look to this one here, you cannot cover this wide range in momentum. So basically from 100 MeV to 100 GeV with one technology. So you need different technologies which you utilize to kind of really identify pions, kaons, and protons on track level. And I will talk about that in a minute, what we are doing there. So here you see the detector again. Again in green, you see all the particle ID detectors. And we have several ones which are completely new and again, world first. So let's look to the backward direction here. There we have a proximity focusing rich detector, which the radiator is aerogel. And then actually what is very interesting is that we use LRPPDs, which is new photon sensors, which are developed actually for EIC right now with a company as these photon sensors. And that is pretty cool because you can use them also to measure time of flight. So you get a very precise measurement of time of flight for a track going through of 30 picoseconds. So it's basically one detector which does two functions, time of flight and particle ID. So you can cover actually from 100 MeV up to 10 GeV with this detector for the particle ID. Then in the center, in the barrel, we use a Dirk. I remind you, there has been till now only one Dirk, which is in the Barbar experiment. We actually reuse the Barbar Dirk bars. We completely modify the photon collection here. We use MAPPDs for this, and we can go up to 6 or 10 GeV pion-kaon separation in the barrel. And then in the forward, in the hadron going direction, we do a dual radiator ridge. There we take aerogel and a gas like C2F6 as radiators, so you get 2 rings in there. You see that here, that is the gas ring, that is the aerogel ring, and you can separate actually pions and kaons up to 50 GeV. What is really absolutely new is that we use silicon photomultipliers as photon sensors. Till today, most of the ridges have used normal standard PMTs. And then all of this is augmented by time of flight in the barrel in the forward going direction. And I explained already for the backward going direction, we use AC LGATs, which are low gain avalanche silicon detectors, which give you 20 to 35 picoseconds. And that is something, again, which has never been done in the world and will be utilized for the EPIC detector. So just to show here a bit, what is actually really where we push the envelope is really this Cherenkov imaging with the different detectors. So these HRPPDs, which we are developing with INCOM, which actually give us also this 30 picosecond timing resolution. And here SciPMs, the single photon detectors, have never been used in a ridge. It's challenging because SciPMs actually have some noise and you want to do single photon detection. So you really need to handle the noise which comes from this detector. Then the streaming data acquisition. So the LHC experiments do streaming now as an afterthought to the experiments. Both ALICE, LHCb, and also ATLAS and CMS are thinking about this, but here we do it absolutely from the beginning. And we are not streaming streams of, we really stream of everything the detector actually produces. So you have here your detector, you have your front-end electronics, then you have some smart boards which collect all of that information, and then you go into your computing farm. And we actually do this because if you have normally a trigger, you select on a response from the detector, and that biases what physics you can do. Here, because we collect everything, Raju in 5 years can come to Elke after we take data and say, I had this smart idea, can you measure this? And because I'm not running with a trigger, I can look back to the data and say, yes, we see this or we don't, and prove or disprove his theory, depending on what it is. And that is something which is actually really extremely powerful. What is also really very nice is we want to integrate AI and ML in all stages. So in the front end, here in the DAM boards, and then of course also in the computing farm. So we want to have a fully cognizant detector so that it basically sends you a message, I need a new calibration, and you go for this. Okay, then we have this streaming computing model where we stream the data, we take the AI, and then we do immediately basically do analysis. And if you're interested in this, we have a whole thing, and I give you here actually the link so that you can read up what we are all planning and doing things. We want to shorten the time between data taking and writing publications significantly because we kind of do that all at once. So then forward detectors and far forward physics. So there is an enormous kind of amount of physics channels which all require that you have detectors which are very close to the beamline. So you have DVCS, you have exclusive J-psi production, spectator tagging in night nuclei, coherent, incoherent vector meson production in EA, the Sullivan process, quasi-elastic, U-channel DVCS, and diffraction. And here I give you what actually kind of physics this is related to. And all of this process requires that you have protons, neutrons, and photons, and hadrons at small scattering angles, which basically miss your main detector. And so you need other detection to do this. And this is what you can see here. So here you see actually the EPIC detector integrated into the interaction region. You see in blue here, the electron storage ring. In this salmon color, you see the hadron beam, you see the RCS here, and you have several detectors here, 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 and here, which are integrated into the beamline so that you can actually really detect these protons and so on going forward. What you also see is, and this is actually reality, it looks like that the magnets are touching basically the detector. It's true, we have 50 centimeters between the detector and the first magnet, which is a real challenge to kind of realize this. So here you see the detectors a little bit better laid out. So you have a 0-degree calorimeter, you have the Roman pots, which are silicon detectors which sit in the beam vacuum, and you have the B0 here. And you see the different kind of acceptances. Why that is critical to have this acceptance, and that means it determines how big your detectors are, is if you have not the 200 MeV, but maybe 400 MeV, you really lose how well you can do your imaging. Same here. So in the action region, the constraints are really also kind of given by, because we are reusing an existing hall. So we have a lot of space constraints which need to be kind of considered. And then we have a large R&D program where you can see here all the different topics which we are doing and the synergies with the CERN program. And I just give you two examples. One is the forward electromagnetic calorimeter, where you see here the scintillating fibers which are embedded into this tungsten powder, and you see the different kind of steps which we have been doing, and we are finalizing this. And the same for the D-Rich, so just for your information what we are doing. So last slides, so the EIC project. Sounds all great, but how long do you have to wait that this becomes reality? So we have done a lot of work. We started in 2002, and with all the different long-range plans and assessments, for example, by the National Academy of Sciences of the physics, the Yellow Report, and we just finished the last long-range plan in the US last year, and again, the EIC was recommended as highest priority to finish it as for facility construction. Here you see the schedule. So you see where we are right now. We just finished actually CD3A, and CD3A basically means start of construction for long lead items. That means things which take a long time to build. The magnet is an example because it takes 5 years to build. So we have to start early to be ready with this. And then the next milestone is in October, we do CD3B, and then we go into CD2-3, which actually CD3 means start of construction. There are some speculations that maybe some of the states might slip a bit because of the complexity of the accelerator, so the design, and also because RIG is running longer than we anticipated, so until the end of fiscal year 25. But overall, we stay very well on schedule. This automatically also triggers an installation schedule. I was asked yesterday, so here you can see when the different detectors have to be ready to be installed, so that in 2032, October, we can start with operations. And we have developed that already all. And then here you see actually all the items which we have been successfully kind of defended for long lead items for the detector. It's the tungsten crystals, it's the fibers, and the steel and so on for the forward hadron calorimeter and the electromagnetic calorimeter for the barrel one and the magnet. So it's actually already something in the order of 40 million of equipment for the detector on long lead procurements. And with that, I think we have this all very well under control. I can only invite you to join us, help us to build the EIC. We can definitely do it, and we need all of you to be successful. Thank you.
There are microphones on, I think, every level, so please use them when you raise it.
Yeah, here's one
Right. Hello. So in the particle identification part where you talk about pion versus kaon separation, your K shots will decay to a pair of pions. So how well this detector can resolve between
Oh, it can easily resolve these pions. Yes, it's not a
so
problem.
from the prompt pions.
Yeah, and also for decay pions from the K short, because you have a decay vertex and then you detect them as well.
So this should be an ideal machine for strange tagging.
Absolutely. Yes.
Okay.
Yes. I would use just K plus and K minus for strange tagging, but you can use K short as well. Absolutely.
Any other questions? Yes, Raju. There is a one, sorry. There are a couple of.
So
It's on.
it's on, okay. Yeah, so, in terms of, this all sounds really fantastic, but what is the physics that you can't do, that you would like to do with this detector that the current, configuration doesn't allow?
From the NIS science, we can do absolutely everything.
From the what science?
From the NIS science, so which was identified in the white paper in the NIS kind of assessment, and we can do more because I have not talked about jets. Jets was not a big topic. We can do very well jets because of the HADRON calorimeters which we have and the fantastic tracking. We can do spectroscopy. So I personally think there's very little which we cannot do. Very often people say, why don't you have muon ID? In our kinematic region, we don't need muon ID because muons are the only particle which are not kind of showering. So if you have a MIP going through an electromagnetic and a hadronic calorimeter, you know it's a muon. As such, we have automatically also muon ID and can do vector meson with the muons as well.
Yeah, so I didn't understand this part about how the muon ID actually works. So
you detect a minimum ionizing particle through the calorimeters.
Okay.
Because in the LHC experiments, you have hadrons which don't shower. We don't have this because our energies are so low, so that hadrons at maximum have 10 GeV in the barrel and something like 50 GeV, and they all kind of are not MIPS anymore. So we can very nicely separate also muons. So we can really do everything.
So you could do like all the bottomonia, like the different bottomonia levels.
Yes.
Okay. So what's the case for a second detector?
Complementarity.
Just complementarity?
Yeah. So if you I think it's very important because you measure things, no machine has ever had only one detector. The B factories were 2 B factories. So, and the LHC has several, and they kind of cross-check each other. And you want to do that here as well, because you will see some things, let's say in the spatial imaging and so on, and if you don't have a cross-check, it will be terrible. And if you take the HERA example, then actually by having H1 and SUS together, because of the different systematics, you gain more than a square root of 2 in the luminosity because you reduce your systematics much more because you have 2 independent measurements. So I think it's absolutely crucial to have a second detector because you want to show that what you measure is not some whatever, but it is reality. So you need a second detector.
Well, it would also be nice to have a science case for something you can't do as well, because
I don't believe in this. If you ask me, CMS and Atlas didn't need different science cases to build both of them. And it is very difficult. So one thing you could think of is that you optimize the detector differently for facility upgrades. And we are talking, Christine talked about polarized deuterium, which is something which we don't do at the first day. So there could be some observable, maybe you choose a certain detector which is better suited to measure this, but it is hard. It's not easy to imagine a different science case.
Great, thanks.
Since I'm a theorist, and it's mentioned, please join us. We have a very big community, in India doing QCD for LHC physics, mostly for a very long time, because EIC is being built actually. So, and which way we can actually join? Because some of us actually started with DIS, like spin physics and things like that, but moved to LHC. And you can see a lot of youngsters, in this. How we can join actually to contribute to any of this physics program?
For the theorists, of course, we have a theory working group in the EIC user group, which has regular meetings. So we have next week, I think, if I'm correct, we have one, for example, on developing Monte Carlo generators, because that will be very important and actually I think it's next week. It doesn't matter. We can, there's also the workshop, but next week we have a meeting, a Zoom meeting. And the thing is, that will be very critical, and theorists can help us with this, because the theory needs to go into this Monte Carlo generators. There's, for example, no good EA generator for DIS. There is nothing really in Monte Carlos for saturation type of physics. So there is an enormous amount of work also to be done there. And then in general, of course, looking for new observables, we were talking about next to leading order, but we could go to next to leading order in some of the observables and things like this. So I think there is plenty of work. And if you really want, I teach you how to build a detector, and then you can join us for that as well. Huh? No problem at all.
I think she showed the distribution of experimentalist accelerator scientists and theorists
I did.
In her user group meeting slide. You can certainly join there. You will get all the information that is needed.
Yeah.
And you have access to the user group theory activity. So that's the best way to do it.
The threshold to become a member of there's basically no threshold to become a member of the user group. You send an email that you would like to be included in the mailing list. And you see we have 360 theorists, and so it's a third of the experimentalists, but that's a large number.
First is just a comment. Two of the conveners of the EIC theory working group are here. One is me and the other is Felix. So you can talk with us. But then the question for Elke is concerning the deuterium. Mm-hmm. So I wanted to ask you, so what are the technical problems to have a polarized deuterium? And if you have polarized deuterium, do you think you can have also tensor polarized deuterium?
Oh, good. Okay, so deuterium has a very different G factors than proton and helium-3. So we cannot use the techniques which we are using to keep the beam polarized. We need to kind of use the RF frequency to keep the deuterium polarized in the machine. That is tricky and far from ever proven, has not been done ever. Tensor polarized deuterium. There's no way to measure. There's no polarimeter for tensorized deuterium. So you can do, of course, you cannot do the thing like we did in Hermes, where we have the two vector states and combine them, and you would have to inject an m=0 state. You cannot measure this. So this is something which is really very tricky. We don't think we know how to do tensorized deuterium. I know why it is important and things like this, but I don't know whether this is really something you can do in a collider. And this is just it's just where how you can measure the different states. Because the beam goes around, it depolarizes, and then you don't know in which direction or in which spin direction it kind of flips to. We also, for the, if we have polarized protons, we don't have 100% polarized protons. So, and if you have no polarimetry to measure this, then you don't know what you have.
Is it the statement, the general statement is that no one has ever polarized deuterium in a collider? Is that true or not?
You have one polarized collider in the world for hadrons. It's called RIC. And there's no other one collider which did polarized protons or polarized beams at all.
Yeah.
So
let alone a deuterium.
There you have your answer. Mm-hmm. And deuterium is the most tricky you can do.
All right. I think we need to go forward. So let's thank Elke.